Cool, I'm just going to do a quick video on how to repair the Kickr circuit board and just a couple of helpful hints. So this is a Kickr 2019 circuit board. Excuse the bird's nest. The reason why it's, I guess, I've had to tap off some different places in the circuit board because the tracks were completely blown off. If you'll see, maybe this track here is actually completely missing. So yeah, just a helpful hint, I guess, if you are testing, just keep the current to about 50 milliamps on a benchtop power supply. Anyway, the basic circuit board is it's pretty simple. It's run mainly off the GEM2 module. In this case, I've just replaced it with the NRF 5283-2 microcontroller. It's quite simple, but it's quite frustrating because it's quite prone to static discharge onto the input-output, which can damage parts of the microcontroller. However, it's not that obvious and it can just cause some erratic behavior. If you look over here, there's actually, this is a 2016 version. And down in this area here, this is the input from the cadence sensor. And you can see it's pretty plain, it just goes straight to the cadence sensor. On the newer version, in the cadence sensor area, there's a bunch of TVS diodes, or transient suppression diodes, to try and stop that static discharge. So an improvement, but for whatever the reason on this board, it still suffered some damage somehow. So that's the diode section going off to your cadence sensor. Obviously, this is your MOSFET controlling the brake. This is a reverse bias diode. It stops the EMF from the collapsing forces when the coil is energized and de-energized when it's braking. Obviously, the main controller, there's two GPIOs that go straight to the red and blue LEDs. On this side, this is our 3.3 volt regulator. And I'll chuck a link below where you can get these off AliExpress. It's not the standard layout, so it can be a little bit tricky to find. And obviously our main smoothing cap and main input. So a couple of points to test straight off the bat is test we've got 3.3 volts coming out of our regulator. That will go straight to our microcontroller, the very first pad down here, I believe. And it also goes straight to our sensor, or in this case our TVS diode, and onto the sensor as well. Once we've tested that we've got 3.3 volts, and even if our red and blue LEDs are coming on, then we can check the cadence sensor itself. Cool, so now for the guts of it, how to program this chip. So if we look at the microcontroller, I've drawn out this diagram, so hopefully it's a bit easier, or at least for myself to follow. But these are the basic functions of the GEM2 module and all the pinouts. So if we look over here, you can see there's 26 and 27. These control the red and blue LEDs. Straight after that is the cadence pin, so that's the one you want to check for your cadence signal. Below that is a temperature. Down the bottom, this is an external crystal, and you can see it on the board here. It's this one here. It's not the main CPU clock, it's just a real-time clock, so a bit of a slower 38 sort of kilohertz crystal probably, but that's a slower clock. The main CPU one being up here. I guess just a point to note, if you are using a module like this, it's got the both clocks built in, so I don't actually need to hook up these to the circuit board anymore. Just walking across, we've got the brakes. It's obviously controlling our brake feedback. And our main power and ground off to the right here, straight to our regulator. For programming, these are the important ones here. So 23 and 22, this is our data and, this is our data clock and our data signal. So clock and data. So these three here, ground, clock and data, that's really what I want to hook up to be able to program. If we see what that looks like on the board, you can see the placement of our module, and just off to the right we've got these lower two pads here. So if we look at these, the top one is going to be our clock and the lower one is going to be our data. So I'm just going to tap off these two here, and I'll probably just tap off here for my ground. It's a little bit messy, but it's essentially what I've done here. It's just harder to see. But for programming, all I'm going to do is those three pins, clock, data and ground. I'm going to power off my benchtop power supply. There's a couple of reasons for that. I guess I can see the current it's drawing, just so I can do a bit of real-time fault finding maybe. And if I want to quickly reset the chip, I can just power off and on there really quick without having to worry about software, whether that's working or not. So first thing I'm going to do is power on my power supply. Obviously you can see straight away that the board's energized, but there's nothing happening, and that's just because we've got that blank chip. However, you can see it is drawing about 18 milliamps, so that's about normal. It's probably what you want for a blank chip, sort of around 18 milliamps. Cool, through my programmer, and if I bring up my J-Link program, and I've got my command prompt, and I'm just going to type connect. Cool, so when I first connect, because I've done this before, it's got my chip saved, but if you don't have your chip saved, you just want to type in NRF 52832 underscore XXAA. Just be mindful of this last part. There's a couple of different versions of chip in there, but that's the size. So the one on the GEM2 module is a 512 kilobyte, so that's the size you want. Cool, I'm just going to hit enter to accept that. I want to use SWD for this particular module. I'm just going to accept the default speed there, 4 megahertz. And as soon as that's accepted, it's going to come up, and you're really looking for this one here, Cortex M4 identified. And that's the real key that it's talking to our chip, and we're connected successfully. What I just like to do, might just be me, but I just like to do an erase cycle, just to confirm everything's sort of working reasonably well. Cool, done, erased. From there, I need to program the UICR. So this is user configuration bits, and this is yeah, I think it just is a little bit annoying doing the cut and paste. It just did it there. It was probably so fast you can't see it, but I'll do it again anyway. But you need to program these configuration bytes, and this is at hex address 1000 1000. These have to be done, and if these aren't done, then your chip probably won't boot, or if it does boot, it won't accept a firmware update, and probably won't boot a second time. It's only a couple of bytes, so it's real quick, but I'm going to program that memory area first. Cool, done. Once I'm done that, I'm going to program my firmware proper. So obviously this is my 512 kilobyte file, a little bit bigger, and it's just loading that now. Cool, so I've got my UICR and my firmware proper programmed. You can see still looks dead because it's still in a programming state. I could just power cycle it now, but what I like to do actually is if I come back here, if I type reset, or this is an older J-Link program, so all I need to do is just hit R, that will reset the board, and now I type go. Cool, I'll just leave that there for a moment, and I'll show you the board. I've sort of got go sitting there on the terminal. As soon as I hit enter, there we go, it comes to life. Searching for Bluetooth, and we've got our power signal, and also our current jumped up a little bit. It's just a little sequence I like to do. Like I said, you could power cycle it, but I just like to really confirm that that is working. And actually I will power cycle it now, just because if those UICR bytes aren't programmed correctly, then it will fail to boot a second time. Cool, and there we go, it looks pretty good. I'm recording on my cell phone, so I can't bring it up, but at this point hopefully I will be able to bring it up on the app and see it on my Bluetooth, that it can connect successfully. It's up and running. You can see it trying to search for Bluetooth, but our power's on. So just to really confirm a bit of fault finding, what we can do is you can use a white piece of paper or whatever, reflector. I've just got a little mirror here, and if I look down at my sensor and I measure the voltage on in this orientation, it's going to be the very right hand piece, and you'll see that it's 3 volts on my meter. As I start to bring my reflector over the element itself, you'll see that voltage drop, and it should drop right down to 0 volts. I take my reflector away again, and it will rise back to 3.2. So that's how the feedback works for the cadence sensor. No reflection, 3.3 volts, and full reflection, 0 volts. So you should be able to trace that through to the microcontroller. If that is in fact happening on that microcontroller input pin, then your microcontroller is probably dead and needs to be replaced because that input is damaged. Just again, so I have tried to change the microcontroller chips straight off the GEM2 module. I've got a couple of replacements here from AliExpress. However, I've only had about a 50% success rate, so I probably wouldn't recommend that. I'd probably recommend either, if you're keen, just going with the AliExpress module, or otherwise just pay the postage and get the GEM2 module from North Pole or Nordic. And summer with voltage regulators, just off AliExpress. Not standard layout, but I'll link it below.